So today we're talking with Ian MacMoy, who is President and Chief Technology Officer for Intermetallic Group. Welcome, Ian. Appreciate you joining us today.
Thank you, Tim.
Yes. So tell us about Intermetallic Group and all that you do and all that you've been working on.
Right. Well, Intermetallic Group came out of probably about 8 years. So 2014 came out of 8 years of hydrogen embrittlement study. Currently, I am the API 20P chair over coatings and platings. API is American Petroleum Institute, and we're taking a deeper look into hydrogen embrittlement, both subsea and production equipment and things like that. So it's plagued us in many ways. So I brought about, after doing root cause analysis for the last, 15 years, I found where the problems were, both internal plating and EHE, environmental hydrogen embrittlement. And that's when I brought, Intermetallic Group to the masses, I guess. And it's a thermal diffusion process that we use to eliminate many of the variables associated with how things are put into the field and the internal coatings and platings that we do.
Gotcha. Yeah, I would assume that in the petroleum industry, any type of failure like this can be catastrophic. I mean, I'm sure you've seen it, and that's kind of what the leading force is that you've got to have almost a no-fail policy with
Right.
this.
Yeah, really do. And it got to a point to where the government got involved. Bessie, Bureau of Safety Environmental Enforcement, they got involved and they said, "Hey, listen, we've got to get a clamp on this." And so they've been very much involved. And the API said, "Look, we're going to make new rules and really hammer down on where these variables are." And that's what we've been doing for, the last 4 or 5 years, really heavy, getting involved and finding it out. The thing is that 3 or 4 out of the 11 issues found were coating and plating issues and variables associated with that, whether it be pre-process of cleaning, which all of your listeners would know about, or if it's post-processes that we're looking at. And looking at where all the problems were, we said, hey, we know we have something different, and that's going to be the thermal diffusion, because it's actually metal that we're putting down instead of a polymer or a fluoropolymer or something like that is normally used in the industry.
Right. Just for those who may not know, and I was just looking at it earlier, intermetallic means what? It means kind of the fusion of what?
Intermetallic is that's a great question. Wow. The intermetallic is what type of structure that we're putting down. Do we have an intermetallic, meaning do we have the crystalline structure? Like I said, we're putting down a surface alloy down on the surface of the substrate of metal. And so instead of it being what we know as a covalent bond or a mechanical bond or something like that, we're really looking at putting down a metallurgical bond. And a lot of what we're finding in that intermetallic is zinc Fe zinc, or we're looking at nickel zinc, that depending on what is needed and is the type of elements we're using to put down on the surface of the metal. So it's a combination of all those elements that we're putting down is an intermetallic.
Gotcha. Take us through some of the research that I know you've made some kind of findings in some of the research that you're going to highlight some of that for us that's been going on maybe for the past year or so that you found.
Oh yeah, well I if I talk to my wife or anybody else, I bore them to hell. But this is something where hydrogen embrittlement, going back into that, really digging down and finding what was causing it, writing many rules and regulations, that type of thing. We broke away from cadmium, 20 years ago, way too quickly. And if you go and look at breaking away from cadmium, you start to see like 11 different properties, which we're discussing in the SAE about nickel cadmium, right? NiCad. and the properties and why it's not outlawed. It's not. It's something. It's because it's really good, and it is an area where we took cadmium and zinc and put them together, and they both interacted and worked with one another to bring about a pretty good product. And that's exactly where I got a lot of my research from. It was, why was it so good? Was it the price? No, it wasn't. It was the fact that the cadmium reacted and oxidated much like aluminum or chrome oxide does, very quickly. And then you had the zinc that backed it up and multiplied it, which zinc does, but it multiplied it a cad zinc. And that's exactly what we needed. And that's exactly kind of what we're doing here. Is we're not only putting down a thermal diffusion, but we're really counting on that oxide that is going to come from that surface metal and what is in the environment. And is it going to be beneficial? Sometimes it is. You have over 80% zinc, you're going to get beneficial products from even the environment. So this is sort of a science. You go and look at stainless steel. If you know, all stainless steel has to have 10% chrome in it by definition. It also has to have a certain amount of nickel in it too. And so when at the surface of stainless steel, which most people know, the chrome oxide oxidizes within 5 seconds, very quickly, hard to plate. But that nickel passivates too and gives sort of a dull and stops any corrosion or oxidation coming down inside of the substrate. And that's a lot of what we're about here. Is we wanted to take that surface alloy technique and apply it on everything surface wise.
Yeah, I was going to ask you. So, what is this process going to be used for in the future? Where do you see it being used?
Wow, it is not something new. We're talking hundreds of years that this has been around. Sheridizing with thermal diffused zinc has been around for over 100 years. And what we're doing is we're doing aluminizing, we're doing zinc thermal diffusion, which is very much like sheridizing. And we're doing also other things. We're putting in barrier metals such as nickel and cobalt. Most of those four are what we're really working with. Chrome is great. We can do chrome, but it really only plates about 5% on the surface. So it's good for CO2, but this is going to be used for H2 solutions for hydrogen, which Houston is taking very seriously with energy because it's part of the petroleum. They carry hydrogen in the petroleum. So we H2 hydrogen. We're looking at the production H2S that we do here. We're also looking at corrosion, wear. Any of that stuff is able to be stopped by the thermal diffusion process in intermetallic.
And I understand this isn't not just a mechanical fastener solution, right? There's other applications that this could certainly well be used for as well.
Right. The mechanical properties are on the surface of the metal. And so we're really looking at a surface solution, right? The surface metals and what properties are in the surface metals. That's really what we're looking at, and what solutions. So you're talking about corrosion, obviously, melting point, so high heat things, electrical conductivity. A1059 of the ASTM is widely used in the pole line hardware. And a lot of that has to do with the electrical conductivity of it. Magnetic properties, again, if you could take a nickel or a cobalt based metal and then diffuse selenium into it, that would be really big deal. So hardness, tensile, ductility, all these things are surface properties that we deal with.
So are you doing mostly research, or is this something that are you not going to develop products that people will eventually be able to buy, but you're doing research for those are your customers are research people, correct? Or you
Actually, we're a bit of both. What we are doing is we're doing production here. We actually do service production. And that's something that with working with this, we have, because we're fairly new, there's not one of us in every town. We do a lot of research and development in order to prove out a new spec. And so whenever you have a new specification or anything like that, you have to prove it out. And the research and development just becomes part of that. And yes, a lot of things are new because we're literally pushing in and growing crystalline structure, both in the top layer of the substrate, where there might be a lot of vacancies, and then growing out from there. So we're really improving a lot of stuff more than making new things.
Well, I know you have a background. You were actually, I believe, worked in a plating shop for many years, and so certainly, people out there who are sort of looking for solutions to certain vexing problems they have could probably get a hold of you. I know your website, intermetallicgroup.com. They can go there. They've got a lot of information. They can contact you. I know you could probably do some consultation with them on that. But what are you looking forward to? What are you working on in the next year or so? What's going to be your at the top of your list?
Top of my list is really we still use a lot of cadmium here in oil and gas, and there's a number of things that we can do property wise to take care of the cadmium if they're not going to use it. Also, chromates are really something that we can't live without, but looks like we're going to push them out. And there's a lot of specs that have already pushed out chromates. And we've taken a thermal diffused zinc and then applied an aluminum sealer over it that seems to be doing very well without the hexavalent or trivalent chrome that we're all used to. So we'll be working on that, and then improving electroless nickel as well, and working with others on those specs.